Okay, let's talk about manufacturing. Let's do the big picture. There are basically about 7 things you got to do to make the enterprise work. You got to have specs. Um, you got to make sure it's going to work just in concept and do some math on it. And then you got to do the product to realize the theory or provide technology to capture the theory. And then you got to cost it out. It's all about money. If it doesn't make sense, don't make it. Just buy it. And then you got to design a process that will make it for you. You start making it, and then you talk to the customers, see what they think of it. So I'm going to clump these four top ones together and just call it product development. This goes from basically, we call it white sheet, an idea that you put on paper, to the actual product. So we're going to enter this picture from the 6 o'clock position, the business analysis. That's kind of like the specification development. What do we have to do to make this thing? What does the customer want? What do you want the product to do? And then again, you do the concept development and testing, and you play around. This is a very critical part. If it doesn't work on paper, it's probably not going to work on real life. Then you do different screenings of different options, and then you do some brainstorming, some ideas on how to make it. How much is it going to cost, right? You'd have a tough time developing a new TV that was going to compete with a TV that's only about less than half that price. It's got to have something. What does it have that makes it special, and why do people pay the extra for it? You start commercialization. Is there really a market for it? If there is, okay, let's go with it. Then you implement the technologies, see how it works, and then you do some market and beta testing. All this is really before you start kicking a lot of money into it. You throw it out there and see if people see what bites on it, right? So next step will be getting into the actual process of making this thing. The next step is process design. And this is kind of like doing some engineering, but instead of developing a product, you're developing a process. And we talked a little bit about lean and things in the previous unit. And we're just going to expand on that a bit. Now, in general terms, the process design, it's basically you're engineering the process. Instead of engineering a product, you're actually engineering some actions and then some things you're doing. So you want to look out there and see what the best practices are. And what does the process have to do? What are the parameters that you have to have done? You're going to have to get some tooling. You're going to have to get some fixtures to hold the product. And you want, if you're a modern factory, you're going to have a computer out there. And you now have the ability to model and see how your process is going to work before you implement it. There's a video in the reading on how McDonald's did their hamburger thing. And of course, you want to get in trouble real quick, have somebody die in your factory, or have a big poisonous gas leak in your factory. So what do you want to do with best practices? And I'm going to show you a link as to the Baldrige Award, and it's all about the best practices. But you got to best practice everything: your strategy, your development of your product or service, your skills. Are you up to the level of everybody else? How's the quality? Can you come up with creative solutions? And how are you doing in the market? Are you having success with whatever you're doing? The tooling and fixturing. If you look at that, we got some tools. It looks like some threads and taps, and we got some fixturing to hold the part that they're putting it into. This is critical. You want a lot of flexibility in your fixturing and tooling. If you get a very specialized tool and need to change your product, that involves a lot of change over time and working. So tooling and fixturing. Again, it's a chance to do some best practicing. What's the best out there? And you can go to outside sources, tool sales, things like that. This is computer integration. This is actually kind of old technology. If you look at those things driving around, what they got is basically marks on the floor, and they follow that. If you've ever been to like amusement parks, the big ones like Disney World and Universal Studios, and you see in those little cars and they drive around, that's all done with computers. And now a lot of things like subways and trams and actually airplanes fly themselves. It's all done with a computer nowadays, and that's the way processes are going. you're going to have a computer or some kind of electronics controlling it. It's not going to be human controlled. What I've got here is a picture of a factory. The thing about it is this factory doesn't exist in real life. It's just a big model. And they can run that factory inside the computer. It's kind of like playing a video game. You know, the world's created and how it operates in itself and things like that. You can do that to the point now where you can actually walk inside the factory. Just amazing, the virtual world. Well, Paul, this is the worst disaster, and a lot of people don't even know about it, but this basically killed a lot of people in India. Worst industrial accident ever. Watch the video. I'll just let it speak for itself. So we're finally ready to go into production, and this puts everything together. You got the best practices, you got the tooling, you got fixturing, you got computer integration, you got your machining and modeling, and you got safety. It's all come together. You're ready to start making the parts. And this is actually a car factory, BMW, and as you can see, it's pretty automated, very modern. And this is the plant layout. Again, you're integrating your production, and it goes back to the very idea that Ford had, putting everything in the proper order, and that's what this is. This is actually a steel mill. I thought it'd be appropriate for Mississippi County. And if you make it, you own it, right? So customer relations. I think everybody should have to spend about 2 weeks in customer service and see what happens when you don't take care of the customer. And a big part of your of what you want to do is make sure the customer is satisfied. But more importantly than that, you can learn from the customer, right? There's a lot to be learned. He'll gladly share information about your product. I'm going to go outside the factory example and talk about concurrent engineering. When we were racing to the moon, Wernher von Braun wanted to do everything in steps. Okay, we got to test the retro rockets. And he'd sent up a flight just to test the retro rockets. Okay, we're going to test the second stage separation. He'd do a flight like that. And it's going to take forever to get to the moon. So what they did is said, look, let's just design all this stuff together at the same time, put it all together, and test 20, 30, 40 things at once in each flight. That's concurrent. So let's go back to the factory. If you're designing a product, at the same time you want to be designing the process. And you want interaction between the people. The Swedish have a name for it. It's called fika, where you socialize and talk with each other. And you get some, well, I'll talk about it in another slide. Give me just a second here. It's called synergy. It's where you get a group of people, a team together, and you start talking with each other, and you find out about each other. And more than that, you come up with new ideas for each other, with each other. And you keep on building on that. And you want a very diverse group. The more diversity you have, the studies have shown the better it is. So concurrent engineering actually results in synergy. Okay, now there are different ways of controlling a process or anything in manufacturing. Let's talk about open loop. Basically, you set some parameter, and that's it. You don't verify the result. No feedback mechanism at all. So for an example, you got a hydraulic cylinder. You set that cylinder to push something 6 inches. That's it. You don't check it to make sure it's done 6 inches. You just assume it's going to do 6 inches. This is called open loop. No feedback. The other type of control strategy is a closed loop. In other words, you have feedback. So taking that same hydraulic cylinder, I wanted to go 6 inches. What I would do is set a transducer or sensor 6 inches down the away from the cylinder, and if it didn't go 6 inches, well, the sensor would tell that to the cylinder, and something would correct itself. Another example is your cruise control on your car. You set it at 60. If it goes below 60, it speeds up. If it goes above 60, it slows down. There's that feedback mechanism. automation. There are different types. There's a mechanization. This is just basically mechanical. In other words, no computers, electronics, or something like that. I'll give an example in the next slide. And then they got the closed loop control. This is where you tie in the sensors and it feeds back. So going back again is if we got that cylinder, it's supposed to go 6 inches, and it doesn't go 6 inches, it'll automatically adjust itself electronically to make sure it goes 6 inches. So, you know, the computer runs the thing. Airplanes fly this way now. So if we're not on the right path, right on the slope, right on the correct landing approach, the computer will take care of it for us. The pilot basically just sits there and just in case something bad happens. But it's basically airplanes. If you get on an airplane today, it's flown by a computer. This is an example of a mechanical automation. This is called the Newcomer engine. It was developed by a guy named Newcomer in about 1712. And what it would do then is basically it'd operate that pump to get the water out of the Welsh coal mines. So what I want you to watch are the valves, right? Those are set to automatically switch on and off, and absolutely no human interaction. So the way this thing works is the fire heats up the water, makes steam. Steam gets blown into the piston. It expands the piston. The valve closes. The other valve controlling the cooling water opens up and cools it off, and it contracts, pulling it the other direction. So just watch this thing. It's amazing. This is over 300 years ago they came up with this. It just blows my mind that they could come up with something like this.
FANUC robots and factory automation solutions have been facilitating industrial production for over 60 years. FANUC is present in 120 countries, including Hungary, assisting key sectors like the automotive industry, for example at the Audi Hungaria Motor Limited factory in Győr, where they are developing and manufacturing cars for the Audi AG and the Volkswagen Group. Audi Hungria is one of the companies with the largest turnover and export in Hungary, producing 2 million engines and 135,000 cars in 2014.
In our experience, FANUC robots work reliably at our factory. We are constantly improving our production and install robots to reach our targets. In environments where we need to work with high pressure or temperature, the robots are up to the task and deliver quality standards, which would not be possible with human machining. Essentially, robots are used for applications too difficult for humans or where rapid machining is required. Our colleagues like working together with robots as they make human work easier by delivering these tasks. It's very important to program these robots correctly, because when problems arise, it's usually not the robot that causes them, but improper programming or the lack of maintenance. Regarding this, I'd like to highlight that FANUC robots are easy to program, dependable, and we have a very good experience with them.
So we got these computers coming in, so it only makes sense that the computers are also at the individual machine level. So let's talk about a few of them. Numerical control, I put that out in there, but basically it's just, I'm not even going to talk about it. If you see one of these, you'll probably see it in a museum. CNC machine, computer numerical control. This has a computer on it, and the computer controls what the machine does. And the computer doesn't need like a PC necessarily. It could be a tape or something like that. These are still out there quite a bit. Direct numerical control. This means that the machine doesn't have a dedicated computer. It's back when we used to use mainframes, that type of thing. We used to be able to wire the computer or the machine into a central computer and control it there. Programmable logic controllers. These are huge. What it does, it uses ladder logic to get different processes done. So it does it in a sequence of steps. Take that class. You want CNC programming and PLC programming on your resume. These are huge. Just take the class. I'm not going to talk about it much. I'm going to have a video showing a CNC machine, what it can do. It's kind of fun to watch. But if you have any questions, let us know. Let me know.